very much thank Professor Kim for her excellent introduction of what Earth system science is all about. In fact, in about 3 minutes, she gave you an extremely accurate and useful history of where we have come with the Earth system. So I'm going to take off from that point, tell you a little bit about the Earth system itself, and why the evidence is extremely strong. We are rapidly, deeply going into a new geological and Earth system epoch called the Anthropocene. So we need to get a slide down. I feel not only a bit more comfortable, but probably a bit safer if I can move around here with this. So let's kick off. I'm going to talk about the origins of the Anthropocene, some definitions of it, and of course what the risks of this new human epoch actually are. So let's start with what Professor Kim was talking about, is our planet is actually a single system that's evolved over 4.5 billion years into the state we have today. And we call it the Earth system, but interestingly, for a long time, science didn't even recognize this as a system. So over the last 200 or 300 years, with the development of contemporary science, we've learned more and more about smaller and smaller parts of the Earth system as we've dived into scientific disciplines. But it's really only in the past 40 or 50 years we've developed a science of the Earth system as a whole. Obviously, it would take very long time perspectives, and for us humans, this is a relevant time perspective. This graph is from an ice core in Antarctica. It goes back about 400,000 years, and you can see the very regular oscillations between ice ages, which are the long, jagged parts down with lower temperatures, and the very short, warm periods. And this encompasses all of human existence. Fully modern humans, we evolved in Africa about 200 or so thousand years ago. Hunter-gatherer societies for about 90% of the time we've been on Earth, and it's only in the past about 11,000 to 12,000 years we've been able to develop agriculture, villages, and cities. So if we look at this last, about 100,000 years in more detail, there you see it, the last ice age, and then the current geological epoch, the interglacial period called the Holocene, lasting for about 11,700 years. If you look at that temperature scale, there's actually a multiplication factor of 2 at the poles. So the global average temperature actually only varied by about 4 degrees between the ice age and the warm period. And that's relevant when we look at contemporary climate change. But this Holocene has been sort of a sweet spot for humanity. We've thrived in the Holocene. We've struggled in ice ages because it's been very cold and much drier in terms of planetary conditions, and much more variable, as you see in the longer term. But one of the things we were looking at in this big international geosphere biosphere program that I was director of for about 6 years was the fact that we seem to see changes in Holocene conditions. So we did a couple of things. We looked at what we called the human enterprise. In other words, how do we describe humans, how we operate, what we do, and so on. And we do it in 12 graphs there. You can see what they are. So it's population, it's economy, it's energy. That's pretty obvious. But we also looked at resource use like fertilizers and water and so on. And of course, communications, which is really important for us now in terms of transport, telecommunications, tourism, and so on. So what came out was quite remarkable. We expected relatively smooth graphs from the beginning of the Industrial Revolution. So each of these graphs start from 1750. We wanted to encompass the Industrial Revolution. What we actually found, what emerged when we saw the data, was something we didn't expect. It was not a very smooth curve, but in fact, a very slow build-up and then an acceleration of human activity in virtually every sphere around 1950, middle of the 20th century. Well, that was pretty interesting results in itself. But then, of course, being basically natural scientists, we said, does this have any impact on the long-term evolution of the Earth system? So what we did then was to look at 12 companion graphs, same time scale, 1750 to 2000, actually 2010. Here, these are updated versions. And we looked at the top 6 in what we call the geosphere, the non-living part of the Earth system. So we have CO2, obviously an important gas, but also nitrous oxide, methane. We have stratospheric ozone. Surface temperature is the only one that's directly climate. And then we have ocean chemistry. The bottom 6 are what we call the biosphere, the living part of the Earth system. And we have ocean, we have coastal zone, and we have land. So you see the shape of the curves looks remarkably similar to the shapes of the curves of the human enterprise. But there are thousands, tens of thousands of scientific papers that stand behind each of those graphs. And when you examine them, as we did in a big synthesis project, they tell you two things. One is, in each one of these 12, we have moved outside of Holocene norms. In other words, we have broken out of the 12,000-year period of stability of the last interglacial. That's without a doubt. The second thing is, the dominant driver in every single one of those curves is human activity. It's not natural variability. So it's really on this basis that we first formulated the idea that we have left the Holocene, and in fact we're in a new geological epoch. But it was up to this gentleman who actually put all this together. So just to go back one, these graphs actually appeared, these are updates that were published in 2015. The original graphs appeared in 2004. But it was in the year 2000, 4 years before these graphs appeared, that Paul Crutzen proposed the Anthropocene. And that was because he was at a scientific meeting where the data that went behind those graphs was being first presented in a comprehensive way. And the people who were presenting it, particularly the paleo people, the people who studied the past, kept referencing the Holocene. The Holocene this, the Holocene that. And Paul was clearly getting agitated. And he was a guy who would sit and think very carefully, and then he would just burst out and attack somebody or something like this. So he was sitting there, I knew Paul very well, and I could see he was building up to something. And finally he had enough of the Holocene, and he just blurted out, we aren't in the Holocene anymore, we're in the, and he actually hadn't thought of the word, and he just sort of thought for a moment and then blurted out, Anthropocene. So that's the origin of the term. And we picked it up quite quickly in the IGDP. And then that's when we actually just said, we need to take this data and systematize it. That's where the graphs came from. Paul suggested at that time that the Anthropocene might have started with the beginning of the Industrial Revolution, which explains why we start our graphs at 1750 and take them through to the present. So that's sort of the origin story of the concept of the Anthropocene. And even at that time, Paul was obviously using an Earth system context for naming this new epoch. But he immediately and instantly put it in the geological timescale, and he proposed it as an epoch that would replace the Holocene. So, what's the sort of poster child of the Anthropocene? It's obviously climate change. So here you see the instrumental record from 1880. And again, you see some activity, but after around 1950 or 60, middle of the 20th century, the temperature starts going up at an accelerating rate. So currently we're sitting at about 1.1 or so degrees above pre-industrial. But remember, that's already a quarter of the difference between an ice age and a warm period, but in the opposite direction. This is way outside of Holocene norms. The mid-Holocene was maybe half a degree warmer than pre-industrial. And the other thing we can say for certain is this is driven by human activities, the increase in CO2, now up to about 407 parts per million. But to understand why we are going into a new geological epoch, again, you need the long time perspective. So this is back to AD 0. This is the time of the Roman Empire. I don't know which Chinese dynasty was in power back then, but obviously there were civilizations in East Asia at the same time. So over that 2 millennia, you can see natural variability in temperature between those bounded limits. So temperature does vary, but within very, very narrow limits. The spike at the end that I've circled is the human-driven change since about the mid-20th century, on the same time frame as a 2,000-year temperature record. So this is extraordinary in terms of recent Earth history. We can actually do some calculations. The increase of carbon dioxide in the atmosphere, the rate over the past couple of decades is about 100 times the maximum rate during the time the Earth came out of the last ice age. CO2 went up from about 180 to 280 coming out of the ice age. And that was fast geologically. But this is 100 times, 2 orders of magnitude faster. For about the last half century now, the global average temperature has risen at a rate about 170 times faster than the background rate over 7,000 years of the Holocene, which is why natural ecosystems are being damaged and destroyed. They simply cannot adapt at that rate of change. But we've also transformed the biosphere arguably as much or even more than we've transformed the physical climate system. I'm going to leave it to my colleague Mark Williams to tell you in much more detail what the Anthropocene biosphere is starting to look like. I only want to summarize on 2 slides, give you a feeling for what it's like. There was a big international assessment of biospheric change, equivalent to the IPCC, but for the biosphere. And it was published earlier this year. They came up with some remarkable conclusions. I've only got 3 here. Nature is declining globally at rates unprecedented in human history. And there are a number of indicators they use to define what decline means. About 1 million animal and plant species are now threatened with extinction, many within decades. So we are headed on current trajectories into the 6th great extinction event in Earth history. But the first one driven by biological species, ourselves. The web of life on Earth is getting smaller and increasingly frayed. This is a good summary of what the Anthropocene biosphere is looking like. Canadian scientist Lachlan Smill puts it really nicely when he looks at all animals on the land surface that have a backbone. That's us, mammals, and it's birds, and it's amphibians and reptiles. If you add up our mass, our weight, we humans are 30% of all biomass of all vertebrate creatures on land. But our domesticates are pigs and chickens and cattle and so on. They're 67%, 2/3. That means all wild creatures left on the land only comprise 3% of the mass of animals on land. That is a good indicator of how much we dominate the land biosphere. This is definitely an Anthropocene biosphere. Well, Paul Crutzen, back in 2000, immediately laid down the challenge to the geological community when he proposed this as an epoch, and he explicitly said in his 2002 Nature paper, this should replace the Holocene. It should be the next epoch at that level to replace the Holocene. Well, the geological community, and more particularly the stratigraphic community, has obviously risen to this challenge. And in 2009, formed the Anthropocene Working Group under the chairmanship of Jan Zalasevic from the University of Leicester in the UK. We've been working for about 10 years now. There are about 34 members of the AWG, and we've been looking at very broad issues, including a lot of social and human issues, and very focused issues in terms of what stratigraphic cores might be out there that says yes or no, we are in a new geological epoch. After 10 years, we had a formal vote. These are the 2 questions. Should the Anthropocene be formalized in the geological timescale? In other words, should it actually truncate the Holocene and extend the timescale out with a new epoch? Should the base or the beginning start date be placed around the mid-20th century, as the Great Acceleration graphs suggest? There's been an enormous amount of work for that, and the vote was about as overwhelming, I think, as you get in the scientific community. The formal vote was 29-4 with 1 abstention, that yes to both questions. So now Mark may talk a little bit more about this because he's more centrally involved. But now the AWG has moved into the 2nd phase, which is to look at specific stratigraphic cores as candidates for the so-called golden spike for the Anthropocene. That process will play out over a number of years. So this is not yet formalization. This is step 1. We have to go through a few more steps. But it's encouraging that it looks like we have an enormous amount of stratigraphic data now that support the formalization of the Anthropocene. That's a couple of things you might want to look at: aluminium, concrete, plastics, and so on. When you look at those 3, you see an obvious breakpoint around 1950. And these are appearing in strata all around the world. It's global, not just in a few places. Okay, so that's sort of the scientific background of the Anthropocene. But of course, by its very nature, it challenges us to do a lot more studying, contemplation, and so on, about the human side of things, because the anthropo, of course, means humans. And so the question now is, what about humans and our systems? And this is an area where Earth system science is just now starting to develop good collaboration with the social sciences, and particularly with the humanities, to study how humans, how we fit in an Earth system context. And of course, that presents some tensions, because a lot of people in the social sciences and humanities are not used to thinking of humans as major players in the entire Earth system. And we Earth system scientists, of course, are in general fairly naive and ignorant of all the wealth of information that is very important that's coming out of the social sciences and humanities. So the next big step in Earth system science is to try to bridge this gap. And we had a hard landing because very soon after we published the Great Acceleration Graphs, we were heavily criticized by these two political scientists from Sweden who said we kept talking about mankind and humans in general, and they said you've actually totally missed the story. It isn't all of humanity that has driven the Anthropocene. It's the fossil fuel-driven, consumption-oriented, globalized economy. And of course it is becoming globalized and spreading fast, but it wasn't created by global humanity or humankind in general. So intra-species inequalities, as they put it, inequalities within the human systems, are part of the current crisis and need to be considered. So that triggered some more work by us. We went back and we redid 10 of the 12 Great Acceleration Graphs where we could get data that we could now split up between the OECD countries, the wealthy Western countries, plus Japan, the so-called BRICS countries, the rapidly emerging economies, Brazil, Russia, India, China, South Africa, and I suspect Korea should probably be put in there as well, and the others, the poorer countries, African countries, some Latin American countries, and so on. When you see that color-coded split, you see, first of all, something quite remarkable. These data go to 2010, so they're a little bit out of date already. But when you look at population, most of the population growth has been outside of OECD countries since 1950. But real GDP, which is a really good indicator for consumption, still 75% of global consumption is dominated by the Western countries of Japan. So it is incredibly uneven in terms of how the Anthropocene is developed and who's responsible for it. And you can see other interesting patterns coming out that are rather different when it comes to resource use and so on. So we're starting now to see a rich internal dialogue in terms of how humanity is differentially driving the Anthropocene. Equity issues then come to the fore. And as Earth system scientists, we try to look at overall patterns. We don't dive down into great detail, but this is one that comes out quite interestingly. First of all, since the two great wars and the depression in between, those were highly unequal societies leading into that period of Earth history. That evened things out, and you can see as these curves dip, that tells you that we have more equal societies. We had sort of a nice period of 2 or 3 decades post-World War II, where societies were much more egalitarian and equal in terms of their incomes. But then from about the 1970s and 1980s, we see a split in the OECD countries between the English-speaking world and Europe and Japan. Where Europe and Japan have managed to keep, by and large, much more equal societies, where the English-speaking world is going toward highly unequal societies. And why does this matter? It gives you a lot of different outcomes in terms of social parameters. So this was work done by some epidemiologists from the UK, Kate Pickett and Richard Wilkinson, really groundbreaking work to say inequality actually matters. It isn't a case of, well, everyone's pretty well off in Australia or the US. Does it matter that people are grossly wealthy compared? Yes, it does, because it appears we have an equity gene in our gene pool that really starts leading to bad social outcomes when inequality gets too big. You can see all those indicators on the left are social problems of countries that are genuinely wealthy. They are not driven by poverty. And the extraordinarily tight correlation between income inequality on the right and bad social outcomes on the vertical axis is quite remarkable. I think it surprised even Wilkinson and Pickett when they found this. So it's extremely tight. You see the English-speaking countries basically on the upper right of that. The only one that actually is so poor in social outcomes is the United States. It's off the line compared to other countries. But you see Australia, New Zealand, and so on. Down at the bottom are the usual suspects in terms of better social systems, Japan and the Scandinavian countries. So this is telling us now that this is part of the important part of the narrative of the Anthropocene, that it's not just humans, it's differential aspects of human societies, and the equity inequality issue looms as a very big one. This leads to a general, again, an Earth system perspective on humans of, are we starting to see system incompatibilities being generated in the human side of the Earth system? And we see that in terms of reactions against science, we see it in the student strikes, and so on. So I'll just go through a little bit of an overview of what we as in Earth System Science, when we look at the human side of things, what are system incompatibilities. To do that, we need to now look in the future of where the Earth system is going. So I go right back to my first slide of the Earth as a single system. Now in the Anthropocene, with the humans becoming the dominant driving force for how this system is changing, what does it look like? Well, there's the graph I showed you earlier of where we are today. That's the climate system with global average surface temperature. And this is obviously human-driven. Where is it going? Well, here are the very classic IPCC scenarios from low emissions in the blue to high emissions in the red. That's out to 2100. So that's only 80 years in the future. And you see the graph spreading out depending on what we do with the emissions. But this is a somewhat, I think, not a very good picture of what it looks, what the future really looks like because of the time scale. Those look like fairly gentle curves. So what I want to do is put those same curves on a 2,000-year time frame. So 2100 is only a little bit further to the right. So when you do that, it looks like that. So the only other time you see a temperature change like this in Earth history is when you have a massive meteorite strike or some disaster like massive volcano outbreaks. This is not normal, and it's certainly not normal for the last 65, 60, 60 million years in Earth history. So you see the Paris targets, 1.2 degrees down there, and we're pretty much committed to those. So we're not going to stop at 1.1. We already have built-in emissions, built from past emissions, built in 2 or 3/10 of a degree. We can't get emissions to zero tomorrow by 2020. So there's no doubt in natural scientists' minds that the lower Paris target is already gone. We can forget about it. We have to struggle to make sure we keep it below 2 degrees. But we're tracking now between 3 and 4, and as I'll say in a moment, the Earth system may take that higher. This is a nasty world. If you go there in 1 century, even modern high-tech society we think is in danger. And even before we reach 4 or 5, cascading impacts in the human system could lead to collapse. That's outside of my area of expertise. I've seen more and more papers saying that we cannot rule out that this is going to be a quite frightening future. What I want to talk about is my area of expertise is in Earth system science, and that is there are tipping points, biophysical tipping points in the Earth system that may make intermediate temperatures inaccessible. In other words, if we start tipping these features, I'll talk about that in a moment, the Earth system will be out of our control. It will be under its own natural dynamic of moving faster and irreversibly into what we call a hothouse state. So that means if we breach the Paris targets, or even if we go toward the upper one, there is a risk that the game is over, that we're heading for 4 or 5 degrees no matter what we do. So it's there's a real sense of why the students have it right, why there is a climate emergency in 2020. Those are what the tipping elements look like. We've actually, in the last decade, learned a lot about them. They're color-coded. They come in 3 types. They're melting of ice, mainly at the poles, also on the Himalaya, and frozen ice and carbon in Siberia. Their circulation changes. And so atmospheric circulation, ocean circulation, the North Atlantic circulation is very important. And loss of major biomes, Amazon forest, the great northern forests in Canada and Siberia. These things are actually becoming active at 1 degree. We've had, in the last 11 years, we've had 3 1-in-100-year droughts in the Amazon. You look at that statistically, it should not happen. They're starting to lose carbon, and they're one of the biggest biospheric carbon stores. Permafrost is starting to melt. At first, it's slow, but it could take off. There's more carbon stored in permafrost than there is in the entire atmosphere. This is a ticking time bomb up in the north. Arctic sea ice, we think we've crossed a tipping point already there. That will probably become ice-free in a couple of decades. And that accelerates warming in the northern hemisphere because open ocean water absorbs more sunlight than ice. Coral reefs, they may have crossed a tipping point. The Great Barrier Reef is 50% dead, the world's largest coral reef, and it's not recovering. Greenland, accelerating loss of ice from Greenland as we speak. West Antarctica is starting to become active too. So we can see a whole range of these tipping points that are now becoming active. Right now, they're small compared to human emissions, but you see the shape of those curves. They're going up at an increasing rate. The interesting thing, and the thing we've only been focusing on in the last year or two, is the fact that these are not isolated. They act as a row of dominoes, where you start tipping some of the tipping elements, and they activate others and accelerate others. So you see where these arrows go. There are some strong connections here, and there's an exceptionally strong connection up and down the Atlantic Ocean. I'll show you in a minute. The key seems to be Atlantic circulation. That could be the real trigger that triggers a massive change in the entire Earth system. This is a paper that we published only about 2 or 3 weeks ago in Nature, and here we're looking at which of these systems, these tipping points, are actually active. It's called sounding the alarm or raising the alarm. And notice how the real integrator there is Atlantic circulation. It affects what happens to the Amazon because it regulates rainfall there. It regulates actually what happens in Antarctica and connects the North Pole to the South Pole. And already we see a 15% slowdown over the last half century in the North Atlantic circulation. That's not a model, that's measured. So that is already slowing down. What is slowing down? Fresh water melting from Greenland and forming a freshwater pool over the North Atlantic Ocean. And that changes the circulation patterns. So we're really putting out, I think, a very strong warning signal that we are already entering dangerous territory. So a year ago, we published a paper trying to put this in a little bit easier way to understand as a cartoon. This is what's called a stability landscape. So if you think of the Earth system as a rolling landscape with valleys and ridges, the glacial, interglacial cycling is at the back of that. So the Earth rolls between the deep glaciers and the little valleys of nice warm conditions for humans. That's the Holocene. But since 1950, we've pushed the Earth out of that system of valleys and ridges, and now we're in a new emerging valley, a hot valley, or so we're somewhere a degree or so beyond the Holocene. This is the Anthropocene. But the interesting thing is we don't know where the Anthropocene is going, because it depends a fair bit on what we humans do and how we respond to the challenges and the risks ahead. So we're proposing that we actually have a fork in the road here, that the future is not going to be always in human control. That if we pass this fork in the road, we are heading for a cliff or a waterfall that we cannot stop once we go too far down that track. That's the tipping cascade. So, when you look at that, what the students are saying is right. In 2020, we are in a climate emergency. The science supports what they intuitively know. Students haven't thought this out, but I thought, when I've talked to a lot of them, this actually is in Stockholm, by the way. The building in the background is the Swedish Parliament. These students are standing within 10 meters of where Greta Thunberg started her strike, less than a year before this massive strike of 15 to 20,000 Swedes. So, you can see what they're saying. The interesting thing is, when I go around and talk to students in Sweden or students in Australia, what really strikes me is that they certainly do not know the science. A lot of them haven't heard of tipping points. This is an intuitive feeling that they're getting, that their future is in peril. And the interesting thing to me as a scientist was, they actually came out with that feeling of the strikes and so on before we really got off our backsides and said, is this really an emergency? And when we did the analysis, only in the last 18 months we've done this tipping point analysis. We said their intuitive feelings are actually backed up by the science. And they make some strong statements. When adults insist on behaving like children, they're talking about the Davos meetings, I think, here. Children have no choice but to assume the role of adults. You're running out of excuses, and we're running out of time. So the Anthropocene, how it unfolds, is not going to affect me individually very much. Some don't have that much longer on the planet. But it's going to affect my daughter, and it's going to affect her children. And they intuitively know that we are letting them down. What do some scholars have to say about this? These are two gentlemen I can highly recommend this, who are system scientists, and they go back to the origins of life on Earth. The first single-celled organism to form on a planet. And look at the wonderful long evolution of this explosion of the biosphere into the wonderful variety of life we have. But they make some really interesting, strong comments at the end. This is the strongest. Our world today is dominated by a global economic system with disastrous social and environmental impacts. They call it predatory capitalism. Not neoliberal, but predatory capitalism. And they know we are the only species on Earth that destroys its own habitat. No other species does that. And of course, we threaten countless other species with extinction in the process. Kate Raworth from Oxford University in the UK actually has been one of the first people that's put together economics. She's an economist with Earth system science. So she calls this her donut economics, where that outer ring is the ceiling. That's defined by Earth system science in the form of planetary boundaries. The inner ring is what we humans need for a good life. We need, obviously, health, food, water, but we also need education, resilience, social and gender equality, and so on. And she calls it donut economics, that we need to steer economic systems to stay within that space. So she puts out a number of key principles, 3 that stuck out to me. Systems thinking. We have to think in terms of dynamic complexity, not linear cause-effect, not simple indicators like GDP. Equity. The system actually needs to generate equity by design. So it isn't the case that after you have a really unequal society, the government has to come in and redistribute incomes. That's really a malfunctioning system. And the biosphere. We should get rid of the word resources. Our economy should regenerate the biosphere by the way it's designed. So there are people out there who say we can actually organize ourselves in vastly different ways. Humanities scholars have a lot to say about this, and I think one of the most powerful statements is from my colleague Vikash Chakravarti from the University of Chicago, who says, look, if we step back and look at it, here's our entire problem. We have built a society that's human-centric. It's all about us. The rest of the world is just out there for us to exploit. But in fact, he said there have been a lot of earlier cultures that weren't that way. They are what he calls zoocentric or life-centric. There's a huge difference between life-centric and human-centric. And that's where we've gone wrong. And he uses some really nice terms like, right now we have departmental thinking. And science is probably the worst of that because we have disciplines, which is one of the worst cases of departmental thinking. But what we need is epochal consciousness. I'm going to give the last word over to the indigenous people of my own continent, the Australian indigenous people. They are the longest continuously operating human culture on the planet. They're also the first seafaring humans, first humans to actually set out deliberately without being able to see land. We think they came to Australia 65,000 years ago during the last ice age, and they've operated very well through that time until the Europeans arrived about a couple of centuries ago. But they have extremely strong ethical guiding principles. And this is from a woman from the Noongar people. She passed away recently, so in deference to Aboriginal culture, one does not name them. We know who she is. But she was an elder who helped guide the WA Aboriginal people. There's the statement. We're only here for a short amount of time. And it's not to get rich and consume a lot. It's to do what we've been put here to do, which is to look after the country. We're only a tool in the cycle of things. We go out into the world and help keep the balance of nature. Notice that Indigenous Australians understood systems. They're talking about cycles, they're talking about balance. It's a big cycle of living with the land and then eventually going back to it. So this gives us these modern, contemporary scholars and Indigenous people are giving us some clues as to the sort of guiding systems that we need. So where is the Anthropocene going? Well, it's a pretty scary future when you look at Earth system science. However, we are a creative, inventive species. We can change fast. My last comment before I close is, I talk a lot about tipping points, but there are social tipping points too in human systems that can happen very fast. The question I pose is, are the students going to be the trigger for a big social tipping point? We don't know. And if we tip, which way is humanity going to go? I'll leave you with those questions. The fundamental question is, where on earth are we really going? Nobody knows the answer to that. I look forward to hearing from my colleagues in the social sciences and humanities to talk a little bit more on where on earth we actually might be going. Thank you very much for your attention.
Okay, as we are running out of time, as Steffen mentioned, but I think we can
Maybe
do
one
or two short questions.
Okay.
Microphone.
Okay, very interesting talk and very interesting talk. So my quick question is that, so do you think we are already on the tipping point?
Yeah, the question is, have we already crossed the tipping point? There is a small probability we have. So I discussed this a lot with my co-authors on those two papers. Most of us think, no, we have not crossed the tipping point. We get pretty scared between 1.5 and 2. And we have a history, and you can see this in the IPCC reports, of underestimating how much and how fast the new system moves. So there is a small but finite probability we're already over the tipping point. I think it's much less than 50%. We're hitting dangerous territory above 1.5, and that's scary because I don't think we're going to make 1.5, as I mentioned. So this is why I think the students intuitively have it right. This really is a climate emergency. It's a difficult one for humans to handle because it's a complex set of arguments. You have to go back from the tipping points to when they actually might start becoming irreversible, which is hard even for non-Earth system scientists to get their head around.
Okay, and just follow this. So if we cross the tipping point, do you have some suggestions for government to how to adapt this?
This for the first time, there's just starting to be some literature on that. There was a paper called Deep Adaptation that came out by Jen Bendell from the UK. Deep adaptation means when you go over the tipping point and you know you're going through a really, really difficult world, you really have to change how you must adapt. I don't have any answers to that. I don't think anybody does. I think that question is only now starting to be addressed in the academic community. It's a really difficult one.
Thank you.
Okay. I think we can entertain one more question.
예, 컨스트에서 배영입니다. 좋은 강연 감사드립니다. 우리 환경의 그 토대는 결국 인간이라고 이렇게 말씀하시는데요. 교수님께서는 이러한 현 뉴스에서 그 환경을 파괴하는 이유에 있어서 그러면 이 지구를 구할 수 있는 그런 해결 방안이 교수님은 뭐라고 생각하시는지 싶습니다.
Can someone translate? I don't have my earphone on.
Yeah, I think his question is if we have any solution to solve the Earth's system problem. It's basic.
Is there any solution to this? Well, the first thing you can say, obviously, is we cannot continue on the same path we're on. There are all sorts of things. Kate Rayworth has some ideas. There are a lot of ideas out there that have been posed about different looking societies that might be able to deal with this problem. The question, no, as we say in English, the elephant in the room, I'm sure other cultures have similar phrases like that, is how do you actually get the transition rapid enough and deep enough from the really entrenched socioeconomic system, globalized system we have today? How do you do that in time? And can you do it without being completely disruptive? Those are questions that we as Earth system scientists ask. We, natural scientists, can't answer them. That's why we need better collaboration with social scientists, economists, humanities scholars of what is possible in the contemporary human societies of today. So you have asked the most important question, and that's one that I think a broader Earth system science that has a full and important role for non-natural scientists, we need to grapple with that sort of question.
또 좀 이제 말씀하시네요.
Okay.
Yeah. Thank you very much. I would like to close this session.